China's new invention could make traditional solar panels obsolete. Not a slightly better coating, not a lab curiosity stuck behind glass at a conference. A material already rolling off Chinese factory lines right now, built into panels that squeeze nearly double the electricity out of the exact same square foot of rooftop. In the United States, a typical rooftop solar panel turns somewhere between 20 and 22.5% of the sunlight hitting it into usable electricity. That means roughly 4 out of every 5 rays of sunlight landing on an American roof are wasted, bounced away, or turned uselessly into heat. That's not bad engineering. It's a hard physical sealing built into the material. Every one of those panels is made from a material called silicon, and after 70 years of refining it, engineers have almost nowhere left to squeeze. The material about to change that math didn't come from a lab. It came from a rock, found in the Ural Mountains of Russia back in 1839, that sat ignored by the energy industry for over 150 years. Before I tell you what changed, guess this. Silicon has a hard physical limit on how much sunlight it can ever convert into electricity, no matter how well it's engineered. What percentage do you think that ceiling actually is? Drop your guess in the comments, because the real number explains exactly why the solar industry has been stuck for years, and it's coming up. Silicon earned its place at the center of the solar industry, honestly. It's reliable, it can sit on a roof through 25 Arizona summers or Florida hurricane seasons without much trouble, and the entire global supply chain is built around it. But it has a limit baked into basic physics, not bad design. No matter how perfectly a silicon solar cell is built, it can never convert more than about 33% of the sunlight hitting it into electricity. That's the number I asked you to guess. And real commercial panels, the ones actually installed on American roofs today, sit well below even that, in the low 20s. Making that silicon isn't cheap for the planet either. Quartz sand gets heated with carbon in a furnace past 3,000 degrees Fahrenheit, refined into silicon that's 99.999% pure, then sliced into wafers thinner than a human hair using wire saws. Every step burns through massive amounts of energy, water, and chemicals, and after decades of incremental gains, an industry leader put it bluntly in 2025. Silicon has basically had all its lemon juice squeezed out. That's the gap the ignored rock filled. Scientists realized they could build lab-made crystals that copy its structure, called perovskite, using cheap ingredients and a small amount of lead. In 2009, a researcher in Japan named Tsutomu Miyasaka built the first perovskite solar cell. It converted under 4% of sunlight into electricity, worse than solar tech from decades earlier. But the material had one property silicon never had. It absorbs light roughly 10 times more strongly than silicon does. A layer just a few hundred nanometers thick, thinner than a soap bubble, can catch as much sunlight as a silicon layer hundreds of times thicker. By 2026, a Chinese perovskite cell hit nearly 28% efficiency under normal sunlight, beating every single layer silicon cell ever tested in a lab. A material that started under 4% had caught up to, and passed 70 years of silicon refinement in under 2 decades. And unlike silicon, perovskite doesn't need a furnace at all. It can be dissolved into a liquid, almost like ink, and simply coated onto a surface at room temperature, more like running a printing press than baking a perfect crystal. Early perovskite had a real problem, though. It was brilliant in the lab and fell apart everywhere else. Humidity could start breaking the crystal down within days. Heat wore down its performance. Even ordinary UV light, the same UV hitting every rooftop every day, slowly damaged the exact structure that made it useful in the first place. Engineers started calling it a lab queen, always 5 years away from being ready, for over a decade straight. The fix wasn't making perovskite replace silicon. It was stacking a thin perovskite layer directly on top of a normal silicon cell, a design called a tandem cell. Sunlight is a range of colors, not one type of light. The perovskite layer on top catches the higher energy blue and green wavelengths, while the silicon underneath catches the red and infrared light that would otherwise pass straight through, uncaught. 2 nets with different hole sizes, stacked together, catching more than either one alone. A tandem panel combining both layers has already hit 29.2% efficiency and 97 watts of output on a panel built at the same industrial size as the ones going on American roofs today. That's nearly double the power from the exact same footprint. If your roof fits 20 panels, switching to tandem panels could nearly double your home's solar output without adding a single extra panel. And some researchers put the tandem ceiling above 45%, well past silicon's hard 33% limit alone. Perovskite's biggest advantage isn't just efficiency, it's how it's made. Because it's applied as a liquid coating instead of grown in a furnace, it doesn't require the clean rooms and billion-dollar equipment a silicon plant needs. Chinese manufacturers reached meaningful production scale as early as 2023, and by 2025 and into 2026, several had pushed into full industrial-scale output, with single factories capable of producing enough panels each year to power hundreds of thousands of homes. One manufacturer's own data shows the coating process produces roughly a third less carbon dioxide per watt of solar capacity than traditional silicon manufacturing, because it skips the extreme heat silicon requires entirely. China's government backed this technology as a national priority starting in 2021, and that backing shows up directly in speed. Industry insiders in China say that support has pushed lab breakthroughs into real commercial products in under 2 years. In the US and Europe, where researchers still have to chase funding, convince manufacturers, and work through certification step by step, that same jump typically takes 5 years or more. American and South Korean companies are chasing hard with their own tandem designs, but they're starting the race after Chinese factories are already running at scale, supply chains already set up, and costs already dropping month over month. The part that makes this shift easier to trust isn't just the efficiency numbers. It's that tandem cells don't throw away 70 years of silicon manufacturing. The silicon layer is built the same way it's always been built. Perovskite is simply added as a coating step at the end of the existing production line, which means the factories, the supply chains, and the warranty systems the solar industry already trusts don't have to be rebuilt from zero. For 70 years, getting more power from sunlight meant squeezing smaller and smaller gains out of the same crystal. Now, a rock that sat ignored in a mineral collection for over 150 years is layered directly on top of that crystal, and it's already producing nearly double the power on the same roof. So here's my question for you. If a 200-year-old rock just quietly rewrote the rules of solar power, what other overlooked material do you think is sitting in a lab or a mineral drawer somewhere, waiting for someone to try the weird experiment nobody thought to run? And that may be just the beginning. China has already shown what happens when perovskite moves from the laboratory to mass production, and the next generation of tandem panels could completely change how much power we can generate from the space we already have. But whether this technology truly replaces traditional solar will come down to durability, cost, and how quickly the rest of the world catches up. If you found this breakdown useful, subscribe for more stories about the technologies reshaping our world. And don't forget to like this video and share your prediction in the comments. The next big energy breakthrough might already be hiding in plain sight.